So let's talk about flu. Yeah, I promise that's going to be an interesting conversation. So first of all, structurally, it's enveloped viruses, which, by the way, listen, envelope is made out of phospholipids. Enveloped viruses are generally very sensitive to physical and chemical methods of microbial control. Does that make sense? Like bleach. As a matter of fact, one of the most resilient human viruses is a naked human papillomavirus. It can be destroyed only using pretty concentrated bleach. Does that make sense? For influenza, a little bit of exaggeration, but let's say you know how some parents are concerned when kids have a flu, that virus will remain on the toys? No, seriously. You know what's the best way to get rid of it? Just stick it out in the sun, or just put it in the storage for a couple of days. It's going to be gone. Influenza does not stick around to surfaces terribly well. That makes sense? Okay. And it is negative single-stranded RNA virus. Important feature of influenza genome, which will become very critical, is that the genome is segmented. Okay, so structurally, virus in its envelope contains two key proteins, which is hemagglutinin, responsible for receptor binding. It's also, hemagglutinin is the major antigen for the virus, and the major antigen that our immune system recognizes. And neuraminidase, which is an enzyme that is essential for egress and to some extent binding to the cell. Okay, now, which letter? Stupid question. So, hemagglutinin starts with H, right? Neuraminidase starts with N. And how do we name influenza viruses type A? H1, N1, H3, N2, H7, N7, H5, N1. Does that make sense? So there are many types of hemagglutinin, never could remember how many. There are many types of neuraminidase, and different strains of influenza basically formed by combining those genes. That makes sense? And what's important to appreciate here, look, this combination of hemagglutinin, which is responsible for receptor binding, and neuraminidase, which is crucial for release of the virus from the cell and to some extent for the entry. Okay? This combination will determine the host range. So there are viruses, for instance, canine flu. There is canine flu. Can't infect humans. Human flu doesn't infect canines. You following me here? Whale influenza doesn't infect humans, and vice versa. Okay? Good so far? Questions?
So then, this does not have to do with the flu, but like with the coronavirus, so they were saying how like big cats were getting the same coronavirus strand that humans had. But how would that be possible?
Probably because there's a huge similarity between the receptor molecules. It was really surprising, but yeah. Since coronavirus that was infecting bats jumped in humans, I'm not particularly surprised that it successfully jumped in cats. And by the way, mink. It infects mink phenomenally well. Okay. Now, what about, we're kind of moving on towards the transmission. So first of all, I'm not even going to put this on the board, but we all know that transmission between humans is respiratory, right? I mean, for influenza virus, you don't have any questions about it? So you look puzzled.
No, I was just thinking about something else, honestly.
Oh, okay.
My head went.
It's okay, it's okay. No, so you look so like respiratory? Is it respiratory? It is respiratory, transmitted between humans. Now, how do we get drastically new influenza strains? Turns out influenza is a zoonotic virus, okay? Strains that infect humans originate in waterfowl, like say geese, okay? And what geese do when they walk around? They poop. They poop a lot. Even when they fly, they poop, okay? So that poop ends up in pig farms, for instance. And it's not, for instance, like, it's just a kind of segue to pigs, because here's an interesting transition. Check this out. In the waterfowl, the infection is gastrointestinal. When pigs acquire the virus, in pigs it becomes respiratory. Okay? And then it goes into humans. So for the introduction of a new strain, this is the pathway the virus has to go. You see? It has to go from waterfowl to pigs, from pigs to humans. Are we clear about that? The best example, 2009 swine flu, went from essentially every large pandemic of influenza is the result of swine flu. It is swine flu. Every time it's pigs that breed a new strain of virus. Does that make sense to you all? Now, what about avian flu? So, can it be this? Quite frankly, I don't think so, because we're not running around inhaling geese poop, okay? But what can happen is the bird flu derived from chickens and turkeys. Now, is that such a huge concern? Well, let's talk about it. So, I don't remember the names of the receptors, and neither should you, but I will explain what happens to when humans get infected with the bird flu. So, bird flu, like H5N1, for instance. I'm going to use that as an example. Don't memorize the numbers. I will not ask these combinations, God forbid. H5N1. Okay? Uses, say, receptor number 1 in bird's GI tract. Does that make sense? So this is the receptor that it uses in bird's GI tract. Now, question is, well, not my question to you. Since humans can be infected with bird influenza, avian influenza, do we have the appropriate receptor? Yes or no? Yes, of course. Simple questions. The key question is where? And it turns out that they have receptor 1 in lower respiratory tract. So trachea, well, even deeper, bronchi and lungs. Does that make sense? Now, here's you walking around the chicken farm with a mop and sweeping the floors, okay? It's all covered with poop, right? This poop gets aerosolized. You get really tired because it's hot, and you stop and you just do this. And you deliver virus particles right into the lower respiratory tract. So far, so good? So you get an infection. Bronchitis or pneumonia, it's really, really bad. The key question is, can you transmit it to other humans? Now, a classic human flu is the infection of upper respiratory tract. Why? Because humans have slightly different receptor, we call it receptor 1 prime, in upper respiratory tract. So imagine I have a bird flu and I cough here. Okay? And you inhale whatever I coughed out. And all this virus that I coughed out of my lungs ends up where? On your upper respiratory tract, which has different receptor. This is why. Listen, this is why avian flu, classic, typical avian flu, is not transmitted from person to person. I actually came up with a pretty clever idea how you can do it. So you need one person to sit, lean back, open their mouth. Another person with a bird flu will lean over, cough directly in their mouth, while the sitting person will take a very, very deep breath. Obviously, this is an extremely artificial scenario, right? It's not going to happen. This is just to illustrate, it's not going to happen. Does that make sense? Now, have you heard about the gain of, from this fuckers in Congress, everybody heard about gain of function experiment. You familiar, like the idea, what is the idea of gain of function experiment? You do some genetic changes in the pathogen to provide it a certain function. People take it as, oh, those mad scientists want to create something that will kill us all. No. The goal of gain of function experiments is to see what type of genetic change will drive a certain phenotype. Does that make sense? Do you understand what I'm saying? So, two scientists, Ron Fouché from Erasmus Medical Center in the Netherlands and Yoshi Kawaoka from University of Wisconsin Medicine, about 7 years ago, something like that, they did gain of function experiments on the bird flu. What they did, they identified mutations in the viral genome that will make bird flu transmissible between ferrets. Ferrets is the greatest model for flu because they cough. Mice don't. Ferrets cough and sneeze and they can transmit virus normally, like humans do basically. Okay? So bird flu is normally not transmissible between ferrets. They change the genome, it becomes transmissible. People just go absolutely fucking crazy about this. Just totally bonkers, okay? Because they think that they created a virus that will just kill us all. Well, first of all, ferrets aren't humans. Second, they managed to identify those changes. And it means that if we analyze bird flu strains more and more, we can say, oh, look, this new strain of bird flu starts to acquire genetic changes that can make it transmissible between the humans. We have to be alert. That was the goal. Am I clear? But what's, in my opinion, funniest part? The virus that became transmissible between ferrets also became less virulent. So ferrets weren't as sick, which is a pretty normal evolutionary trade-off. It's like, it happens all the time. Does that make sense? So questions about bird flu transmission. Basically, virus binds to something that we have in the lower respiratory tract, but not upper. Okay? Few other ideas about flu. First of all, treatment sucks. Everybody is familiar with Tamiflu. Well, guess what? Virus developed resistance to it. Okay? Almost all strains flu are now resistant. There's a new drug called Xifluza. I don't remember what it inhibits. The point is, all those drugs, they are most effective if you take them first 24 hours after the onset of symptoms, which often is really, really hard. And for Tamiflu, it was the best story ever. Basically, if you take it first 24 hours, it will shorten the length of symptoms by 1 day, on average. And if first 24 to 48, by half a day. So like you're going to be sick for 5.5 instead of 6 days, which I don't know if it's like reasonable result. Okay. What about vaccine? Why do we need to get a new vaccine every year? So this is a really nice explanation. First of all, this is RNA, right? Remind me, please, we were talking about it in Unit 2. Synthesis, process of RNA synthesis. Is it efficient or not? Sorry. Is that reliable, like error-wise or not?
No.
No, there are a lot of errors, right? So influenza, as it replicates through population, spreads through population, which with each round of RNA replication, it will acquire a certain number of mutations. And this accumulation of in RNA molecule result in so-called antigenic drift. Drift being used as the word describing something slowly happening. That makes sense? So for instance, anybody knows what's the predominant type of flu that circulates? Now it's H3N2, and second one is H1N1. But the H3N2 strain that circulated a couple of years ago was different than the one that circulated 4 years ago. Am I clear? Because of the drift. You following me so far? Now, this is why every year, and we'll get back to this. Basically what happens, you have this is hemagglutinin here. See that? Hemagglutinin. This is the head of hemagglutinin. This is the stalk, it's official terms. Antibodies that we produce after the vaccination, they bind the head. Okay? Now imagine there is an antigenic drift, and this is what happened. Does the head look similar? Well, this and this, do they similar?
Yeah.
Are they the same? No. So antibodies, do they bind to this? To some extent. Not great. Make sense? This is what antigenic drift leads to. Another interesting feature of influenza genome is this. So imagine that John has 8 cards that are all spades. I have 8 cards that are all diamonds. Okay? So you represent 8 fragments, 8 genomic fragments of one virus, and I represent 8 genomic fragments of different viruses. You with me so far? We put our stacks together, shuffle them, deal 8 cards to each other. He has spades and diamonds in his deck, and I have spades and diamonds in mine. Does that make sense? It's called reassortment of genomic fragments. It's called antigenic shift. Rapid, dramatic change in antigenicity. Essentially, every flu pandemic was the result of antigenic shift. In 2009, what happened, look, now, don't take my words to the bank, I don't remember how many, but if my memory serves me well, there were 2 bird viruses and 1 pig virus that exchanged the fragments. And you've got a new strain, okay, it was still H1N1, just very much reassorted with different antigenic properties which sweep through the population because we didn't have any antibodies to it. It doesn't mean that the virus becomes more deadly per se, just means we don't have population immunity against it. You see what I'm trying to say? So yeah, it's going to happen. Last little bit, always question, do we need to get vaccinated? How good is the vaccine? Vaccine is not great. Flu vaccines are bad. They have efficiency of about 60%, but here's the kicker. By vaccinating, you're not only serving to yourself, like protecting yourself from potentially dying, because several thousand people die from flu every year. You're also serving to the community because you reduce the circulation. Okay? And basically now, the main goal of the influenza virus research is to make a vaccine that will not respond to the head of hemagglutinin, which can change, but to the stalk, which doesn't. You see what I'm saying? That's one. And two, you are now immunologically educated, so I can talk to you like fellow immunologists. Flu vaccines that we use, those injectable ones, they provide really good antibody response and almost no T cell response. So if infection already happened, immune system has nothing to do about it. mRNA vaccines like Pfizer and Moderna vaccines against coronavirus, they produce phenomenal T cell response, just absolutely mind-blowing. So now there's in pipelines, there's a influenza vaccine, mRNA influenza vaccine, and keep fingers crossed, maybe finally we can get a vaccine maybe once every 3 years, and possibly if they can kind of modify it to include a stock, maybe we'll get universal influenza vaccine. I mean, I would go with like every 5 years, some modification, so we don't have to race against the clock every year, risking to make a mistake. Questions? No? Okay. We'll wrap it up.